Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 42, and it is entitled Phase Changes. We'll begin with a simulation. In this simulation, I have a substance. In this case, it is argon, which is at a very low temperature, which is in its solid phase. This argon is a clump of matter that is contained inside some cylinder. There's a thermometer there that measures absolute temperature, and you can see that the molecules, the particles of this substance are in vibration, but they're not moving enough. The vibrational energy is not enough to break them apart. This substance would be difficult to compress. Its volume is fairly fixed. We call this a solid. If I go and show what the liquid phase looks like, you'll see that these particles here have more energy, more internal energy, in other words, kinetic energy, and they don't have quite enough energy, all of them, to break apart from each other, so they are still congregated together, but there's not this fixed shape that they have. So liquids can take the shape of their containers. Let me go to the gaseous phase here now. In this phase, the substance has enough energy, the particles have enough kinetic energy that they're able to break apart from each other, and they essentially fill up the container that's holding them. And if I were to remove some energy from these substances, which I'm going to do here by taking some ice and putting it in the container, putting it against the edge of the container, then as the substance cools, then the kinetic energy of the particles changes, and as that kinetic energy changes, then there is a phase change from the gas to the liquid and from the liquid to the solid. So I've gone from one type of phase and removed energy. If I add heat by taking this fire and putting it at the bottom of the container, then I can go from the solid to the liquid phase, and adding more heat again, I can go to the gaseous phase. One cool thing about this simulation is that it's possible to look at several different types of substances. Argon you can think of as an ideal gas that has massive particles. This simulation allows you to look at neon as well. So here's neon. The particles are less massive. It's possible to look at oxygen. Oxygen here is a diatomic molecule, and not only are the particles free to translate, but they're also free to rotate as well. And there are some energies that are associated with that rotation and the vibration. You'll not be concerned with those on the AP exam in May, but you will see them if you take a thermodynamics course, and those are considered other degrees of freedom. You'll hear that term referred to. And another cool one is water. So here are water molecules. Not only does water molecules are able to translate, but they can rotate, and they are not symmetric in the sense that oxygen is symmetric. There's some hydrogen bonding that can occur, so there's all kinds of complicated things. But let's go through the phase transitions here. We're at the water with the gaseous phase. Now I'm going to remove some energy, and the water molecules begin to clump together to form the liquid phase. Let me remove a little bit more energy. And as I remove that energy, you can see that the water molecules form this liquid here. They congregate together. And now as I remove more and more energy, you can see that the hydrogen bonding in the water molecules causes the solid to actually take up a little bit more space than the liquid does. There's this open structure that's formed. You don't need to know about that for the AP exam, but I think it's kind of cool. Let's see if I can get this all the way down to absolute zero so that there's hardly any vibration at all. And here I am at 8K, 7K, 6K. I don't know if I'm going to be able to get it all the way down to absolute zero. But you get the idea. The less and less temperature the substance has, remember temperature is a measure of the average kinetic energy, then the less and less motion that the object has. There we are, all the way down to absolute zero, and it looks like somebody there has still got a little bit of vibration. You ought to know the three main phases of matter, solid, liquid, and gas, and you ought to know what characterizes these phases. And I've jotted down a few notes here about them. Solids have a fixed volume. They're not really going to change their shape that much. They only have vibrational energy. The particles just vibrate in place. So their temperature, you remember the temperature is a measure of the average kinetic energy if you talk about the absolute temperature. The liquid has a fixed volume. I can't really change the volume of the liquid by changing the shape of the container. The liquid is a fluid, so it can change its shape if I slosh it around because the particles are not fixed with respect to each other, and it will have more energy per particle than the solid does because of the fact that it can translate. The liquid particles can move past each other. The gas, its volume is defined by whatever it is that is containing it. It's a fluid and has translational energy. And again, these substances that have structure, like the diatomic oxygen or the water molecules, may have other kinds of energies, but you're only going to be dealing with ideal substances that are little spheres, and they only have kinetic energy that you have to worry about. You should also know what are the names of the transitions between these phases of matter. And here is a diagram showing these names of the different transitions. Enthalpy, for our purpose, refers to energy. I suppose that these names are familiar to you. Probably the one that's least familiar is the transition between solid and gas. So dry ice, solid carbon dioxide, will sublimate. It will go directly from a solid to gas without going through the liquid phase if it's at atmospheric pressure. And if it goes from gas to solid, it's called deposition. You also have a transition between the gas and plasma phase, ionization or deionization, but that's not something that you need to worry about. What you do need to think about is what's going on when heat or energy is added to the system. For our purposes, two things can happen. One is that the temperature of the substance can increase. And we've dealt with that when we talked about Q equals mc delta T. How much will the temperature increase? Well, it depends on the substance that you're adding it to. The more mass you have, the higher the specific heat, then the higher the change in temperature is going to be. We've dealt with that in a previous lesson. What we want to focus on in this lesson is when I add heat to a system, it's possible for me to change the phase of the system. The equation we're going to use for that is Q is equal to m times H, where H is going to represent the heat of transition. The heat of transition could be the heat of freezing, or the heat of melting, or the heat of vaporization, or the heat of condensation, or the heat of deposition, or the heat of sublimation. The units are going to be in terms of the amount of energy needed to make the transition per mass of the substance. So it will be joules per gram, or calories per gram, or joules per kilogram, or some appropriate set of units for the substance in question. While the transition is going on, and this is a very important point, the temperature remains fixed. Ideally, that's the way that we're going to solve the problems that you have. So as I pour more and more energy in the form of heat into the substance, if I am at a phase transition, what happens is that energy goes into increasing the internal energy of the particles so that they're able to change their state. I'm not increasing the temperature of the particles. What I'm doing is essentially breaking the particles free or causing the particles to congregate with each other. In your textbook, there's given a table that shows you some heats of fusion and vaporization for various substances. This is table 42.1 in your textbook, and you'll want to use that when you solve some of these problems. What we'd like to do now is to solve some numerical problems, and there are 3 of the 4 examples that we're going to take a look at. So let's begin. Find the minimum heat required to raise the temperature of 470 grams of ice from negative 50 degrees C to water vapor at 350 degrees C. When you solve these problems, one question you want to ask yourself is what's going to happen to the substance during this process? In this particular process, I start with a solid that's at negative 50 degrees C. This solid, I have to warm up until it gets to the solid-liquid temperature transition point, which is 0 degrees C. So I'm going to take some heat to heat up the solid. Then I've got to change from the solid to the liquid. That's a phase transition. So there's going to be some heat that's required for that, and that heat is only going to change the phase. It's not going to change the temperature. Once I get this mass of ice changed into a liquid, then I'm going to warm up the liquid from 0 degrees C up to its transition temperature, 100 degrees C. And so there's heat that's involved with that. Then that liquid is going to stand at 100 degrees C until I have changed all of the liquid until a gas. So there's going to be another phase transition that occurs. Once I've got all that mass changed into a gas, then I've got to heat up the water in the gas form until it's up to 350 degrees C. So I have to account for all of that heat during this process. So in this process, I've got 5 different heats that I need to account for. I've got to warm up the solid from negative 50 to 0. I've got to melt the solid. The temperature doesn't change then. Then I've got to warm the liquid from 0 to 100 degrees. Then I've got to vaporize the liquid. And then finally I've got to warm the gas from 100 degrees to 350 degrees. So I need to write down what the equations are for each of those things. Let's do them one by one and then add them all up together. In warming the solid, the amount of heat that's required to do that is going to be mc delta T. M is the mass, and this problem is 470 grams. C is the specific heat of the solid, and your authors have reprinted for you table 14.1. They've put it on page 364 of your textbook, and they're showing you what the specific heat of water is when it's in its solid state. That's not the same as the liquid state, so you need to pay attention to that. And then the change in temperature is going to be 50 degrees because I'm going from minus 50 to 0. Now, let me make a point here about units. When you deal with units, if you're talking about changes in temperature, then the size of the centigrade and Kelvin steps are the same. So the first amount of heat that I need is 49,000 roughly joules. Now let's melt the solid. The amount of heat that's needed is the mass of the substance times the heat of melting, or sometimes also referred to as the heat of fusion. For solid water, you'll look at table 42.1 in your textbook, and you'll find that that transition takes 334 times 10 to the third joules per kilogram. So it takes just under 160,000 joules to do that. All right, so now we've got the solid changed into a liquid. We need to get the liquid warmed up to 100 degrees Celsius. In other words, I'm going to change by 100 centigrade degree steps or 100 Kelvin degree steps. So I'm going to say Q is equal to mc delta T. Now I'm going to use the specific heat of the liquid, which in this case is 4,200 joules per kilogram degree C. So it takes just under 200,000 joules to warm up the liquid. Now I've got to vaporize. So again, I'm going to say that the amount of heat for that is the mass of the substance times the heat of vaporization. That heat of transition is given again in table 42.1, and for water, that looks like it's 2,260 times 10 to the third joules per kilogram. So just over 1 million joules. There's a lot of heat required to vaporize that liquid. Finally now, we want to warm the gas up to 350 degrees C. So we'll use mc delta T, where now we're going to use C for the gas. And for water, in its steam phase, that's 2,000 joules per kilogram Kelvin, or 2,000 joules per kilogram degree C. Since we're starting at 100 and we're going to 350, the change in temperature is going to be 250 degrees. So we'll end up with 235,000 joules needed for that. So, how much total heat do I need? Well, I'm going to add up all of these numbers that I've just calculated. The amount of heat to warm the solid, the amount of heat to melt the solid, the amount of heat to warm the liquid, the amount of heat to vaporize, and the amount of heat to warm the gas. And I'm going to get some total number. And I get that the grand total is 1.7 times 10 to the 6 joules, 1,700,000 roughly joules, to take this solid chunk of ice at negative 50 degrees C and to turn it into steam at 350